Guys, today we are going to be looking at a scenario and solving 3 problems related to that scenario. So let's read the scenario first. The function fn of x, where n is 0, 1, 2, ... is defined by the following 2 functions. The first function is f0 of x is equal to 1, and fn of x is equal to 1 plus integration 0 to x of fn minus 1 t plus t times the derivative of fn minus 1 t dt. And our first question, remember we're going to be solving 3 questions related on this scenario, is find f of 1 x, f of 2 x, and f of 3 x. So if you want to give this problem a go, feel free to pause the video. Alright, so assuming you didn't know how to solve it, I'm going to go over the solution right now. So hopefully it wasn't too hard since you're just substituting the values of n, 1, 2, and 3 in mainly this equation, right? Because we have a fn. So when it talks about fn of x, what does that mean? Well, you can kind of say it's like a series, right? Because this would be kind of like one term, this would be another term, this would be another term, and it would keep going. All these terms are going to be different. And that depends on the value of n, right? So, So let's start replacing. We know that f0 of x is equal to 1. And let's try first finding f1 of x. So that's f1 of x. I'm replacing n equals 1 in this equation. So let's label this 1 and let's label this 2. So f1 of x is equal to 1 plus integration 0 to x of f1 minus 1, which is just 0, t, plus t times the derivative of f n minus 1, n is 1, so that's 0, t dt. Lucky for us, we know the value of f0 of t, which is just 1. So 1 plus integration 0 to x, 1 plus t times, well, the integration of f0 of t is simply 0, right? Because we know f of 0 is t, f of 0 t is 1, and integration of 1 is just 0. So times 0 dt. Simplifying this, we get 1 plus integration 0 to x, 1 dt. Integrating this, we get 1 plus x. That is the value of f1x. So let's just highlight that. Now let's try to find f2 of x. So once again, same procedure. That's basically saying f2 of x is equal to, substituting in this equation once again, 1 plus integration 0 to x, f2 minus 1 is just 1, t plus t, integration 1 of the derivative t dt. Solving this, lucky for us, we already found f1 of x, so we can just replace it in here, right? 1 plus integration 0 to x of 1 plus x plus t times, now what's the derivative of f1 of t? Well, we know the derivative of this is just 1, right? So let's just write 1 dt, 1 plus integration 0 to x plus t plus 1. Simplifying this, we get 1 plus integration 0 to x, 2t plus 1. Integrating this, we get 1 plus t squared plus t, 0 to x. Simplifying, 1 plus x squared plus x. And if we put it in the standard form, it's x squared plus x plus 1, which is equal to f2 of x. Now we have found f1 and f2. Let's go on to find f3. Once again, same exact procedure. Let me copy this. Let's go up. We're going to use this once again because that's basically where we're replacing our values of n. And right now, our value of n is 3 because we did 1 and 2 already. So that's, actually let me make this a bit bigger. Okay. Now we're on n equals 3, so f3 of x is equal to 1 plus integration 0 to x of f of 2t plus t times f2t, the derivative, dt, 1 plus integration 0 to x. Once again, we know the value of f2t, which is this. So let's replace that. We get t squared plus t plus 1. And then the derivative of this is just 2t plus 1 dt. Simplifying this, we get 1 plus integration 0 to x, t squared plus t plus 1 plus 2t squared plus t dt. Once again, we're simplifying 3t squared plus 2t plus 1. Now we can take the integration. 1 plus t cubed plus t squared plus t. Simplifying this, we get t cubed plus, this is 0 to x, so that's basically 1 plus x cubed plus x squared plus x. And putting in the standard form, we get x cubed plus x squared plus x plus 1, and that is f3x. Okay guys, so now we found f1x, f2x, and f3x. So we are done with our first part. Now let's move on to the second part. Assume f and x, then prove it by mathematical induction. So they're saying that, okay, assume that this is true. So assume this is true because this is f and x, right? But we have to prove it now. So once again, pause the video and give this problem a go. Alright, so I'm going to walk through the solution with you guys. What we're going to do, we're going to assume that this f and x is equal to 1 plus x squared plus xn. And why is that? Well, I'm not sure if you noticed, but over here when n is equal to 1, there was a 1 power, like a power of 1 over here. When n was equal to 2, the highest power was 2. And then the second highest power was 1, and the lowest power was 0. When n was 3, the highest power was 3, the second highest power was 2, the third highest power was 1, and the last power was basically 0. And you can see it follows the same pattern. So for example, if we were to find f4x, that would just be equal to x to the power 4 plus x to the power 3 plus x squared plus x plus 1. Because it's following a pattern. That's how we get this. Whoops. So now that we have that out of the way, let's prove this when n is equal to 1. So when n is equal to 1, let's prove that f of n is actually true. So when n is equal to 1, f1x is just 1 plus x, right? Because if we replace 1 in for n, we get x, and then we still have this one, so 1 plus x. And this is true because, remember, we got 1 plus x from here, but we also got 1 plus x from here, right? And this one we got in the first part when we used the original f and x. So we know this is true. So that's proved, but that's only proved for when n is equal to 1. If n is equal to k, like when n is equal to k, then we know that fkx is supposed to equal 1 plus x squared plus plus xk. It's the same procedure as we replaced n for 1 over here. And that's the same thing for when n is equal to k plus 1. So when n is equal to k plus 1, fk plus 1, x is supposed to equal 1 plus x plus k squared plus dot 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 plus xk plus xk plus 1, right? So let's assume that when n is equal to k, this is true. Let's assume that that's true. Now, if this is true when n is equal to k, we have to prove that this is also true when n is equal to k plus 1. And if we do prove it when n is equal to k plus 1, then that automatically means that this whole equation is also true when n is equal to k. So let's try that. We know that fk plus 1 x is also equal to if we use this, right? So then that would simply be 1 plus integration 0 to x f of k t plus t f of k prime t and then dt. I just replaced k plus 1 in here and this too. Now what we can do, let's start replacing this. We know fkt from here, fk from over here, my bad. Fk is this, right? So let's start replacing that. We get that we're going to need a lot of space. So it's equal to 1 plus integration 0 to x of fkt is over here. Let's start replacing that. So 1 plus x squared plus dot 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 xk. That's fk of t. Now we also have to introduce this, t. Let's take the derivative of fk of t, which is this whole thing. That would be derivative of 1 is just 0, derivative of x is 1, derivative of x squared is 2x, and then over here there's going to be an x cubed when following the pattern. That's 3x squared plus dot 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 k x k minus 1, and then big brackets close dt. Now that we have that, let's start simplifying. This is just 1 plus t squared plus, there would be a t cubed, dot 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 plus tk. Expanding the t, we get t plus 2t squared plus 3t cubed plus dot 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 plus k t to the power of k dt. Further simplifying it, we get 1 plus 2t plus 3t squared plus 4t cubed dot 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 k plus 1 t to the power of k. How I got this last term, I just took the tk out of both of them and I got k plus 1 tk. Now let's just solve the integrand. So 1 plus, the integration of 1 is just t, integration of 2t is t squared, and then it just keeps going on and on, dot dot dot. Integration of k plus 1 tk is tk plus 1, 0 to x. Let's further simplify this, so let's replace that for x. So we get x plus x squared plus x cubed plus x to the power 4, dot 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 plus x to the power k plus 1. We don't need the 0 because we know that if we replace 0, it's just going to all cancel out to 0. Then this, removing the parentheses, let me just do that right here. You would get this. And this looks a lot like what we wanted. Let me highlight this. This looks a lot like what we wanted over here. Right? So hence we proved that when fnx is true, we proved that it is true by mathematical induction because we saw that this, which we assumed, and this, which we got when we assumed that n is equal to k plus 1 over here, is in fact true. Alright, so we're at the last part of the problem, and this part of the problem is maybe kind of tricky, but nonetheless, I'm going to read it. Given fn of t is equal to integration 0 to t fn x dx. Find the limit as n tends to infinity, integration 0 to 1 fn t dt. And if you want to give this problem a go, feel free to pause it. Alright, so I'm going to go over the solution. So from that previous problem, part 2, we saw that fnx is also equal to 1 plus x squared plus dot 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 plus x to the power of n, as we saw over here to our right. So let's try to find capital FNT. Why? Because we know we need capital FNT in order to find the limit, right? So let's start by finding that capital FNT. Lucky for us, they gave the value of capital FNT in terms of that lowercase nx, which we already have here. So let's just replace that. So f capital n of t is equal to integration 0 to t. Fn of x is just 1 plus x squared dot 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 plus x to the power n dx. Let's simplify this. We get integration x plus x over 2 squared plus x over 3 cubed plus dot 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 plus x to the power n plus 1 over n plus 1 and 0 to t. Simplifying this, we get t plus 1 over t squared. Let's just write it like this. I think it would be easier. Plus 1 over 3t cubed plus integration plus replacing t, we get 1 over n plus 1, t to the power n plus 1. So now that we have capital FNT, let's start replacing it in this, the thing that we're actually supposed to find, right? So let me just copy that. Whoops. Okay, well that will do for now. Okay, now replacing that, we get limit as n tends to infinity of integration 0 to 1. Capital FNT, which is just this, we already found that out. Let's replace that. T plus 1/2 t squared plus 1/3 t cubed plus dot 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 plus 1 over n plus 1 t to the power n plus 1 dt. This is equal to limit as n tends to infinity of 1/2 t squared plus 1/2 times 1 over 3 t cubed plus 1 over 3 times 1 over 4 t to the power 4 plus dot 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 1 over n plus 1 times 1 over n plus 2 of t to the power n plus 2. And I'm just going to simplify this a little more. Well, not really simplify, just put it in a more neat manner. What I'm saying is that 1/2 t squared plus t cubed over 2 times 3 plus t to the power 4, 3 times 4 plus dot 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 t to the power n plus 2 over n plus 1 and n plus 2. And now we have that 0 to 1. Let's start replacing that. So we get limit as n tends to infinity of 1/2 plus 1/6 plus 1/12 dot 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 1 over n plus 1 n plus 2. We already did that. And we can write this another way. We can write this as 1 over 2 times 1 plus 1 over 2 times 3 plus 1 over 3 times 4 plus dot 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 plus 1 over n plus 1 n plus 2. It's the exact same thing. I just split 6 into 2 and 3, 12 into 3 and 4, just like over here. So not much of a difference at all. Now that we have this, let's ignore this limit for a second. Okay, let's just focus on this. We can't really simplify this anymore now, can we? Because we have an n over here, we have n plus 1, n plus 2. But even if we replace n tends to infinity over here, you get 1 over infinity. And that's really not what we want, right? We want an actual concrete number. So we still have to try and do some more steps in order to get an actual concrete number. So what we're going to do, we're going to let 1 over n plus 1 times n plus 2 equal to a over n plus 1 minus b over n plus 2. And you will see why in a second. But let's just focus on solving for a and b. Let's multiply both sides by n plus 1 times n plus 2. So that's just 1 here. It's equal to a n plus 2a minus b n minus b. Let's take the n out of these two terms. We get a minus bn plus 2a minus b. We know that there is no n on the left side, so we know a minus b has to be equal to 0. And we know that 2a minus b has to be equal to 1, right? 2a minus b has to be equal to 1. Solving this, let's just, this is basically minus a plus b is equal to 0. 2a minus b is equal to 1. It's just a system of equations. A is equal to 1. Replacing that once again, we get b is equal to 1 too. So a is equal to 1, b is equal to 1. Therefore, we can replace it back in here. So we can say that, let me just, oh my gosh, why does it always come like this? We can say that this is equal to 1 over n plus 1 minus 1 over n plus 2. And I got that from using this over here, because we found the values of a and b, so I just replaced it. Now, let's replace it in this whole thing, including the limit this time. And remember, this was equal to this, all right? We didn't include the limit that time, so we still have to include the limit right now. So limit of this is going to be 1 over 1 minus 1 over 2. And how do we get that? Well, I'm replacing, this is n tends to infinity. So first I'm replacing n is equal to 0. And we know n can be equal to 0 because all the way here, it said for us, n is equal to 0, 1, 2, 3, and beyond. So I'm replacing n is equal to 0 first. Let me get a new page. And I replace it on this side. Okay, so I get 0 over here. So I get 1 over 1 minus 1 over 0 plus 2, which is 1 over 2. Now let's take n is equal to 1. Replace n is equal to 1 here. You get 1 over 2 minus 1 over 3. Replace n equals 2 over here. You get 1 over 3 minus 1 over 4. And that could keep going on and on until we reach the last term. The last term we saw was this. And basically, that's the same exact thing as over here. So I'm just going to rewrite this as it is, because this is the same thing as this. So that's 1 over n plus 1 minus 1 over n plus 2. All right, now we can see a lot of stuff is canceling out. We see that this cancels out with this cancels out with this will eventually cancel out with the 1/4. A lot of terms will start to get canceled. This term will cancel with the term before it, but we're left with this and this term. So let's rewrite this. We get limit n tends to infinity of 1 over here minus this, 1 over n plus 2. And then this is just equal to 1, because if we replace n for infinity, this becomes 1 over infinity, which is just 0. So we get 1 minus 0, which is just 1. So that is our answer. So I'll see you guys next time with another problem. Bye!